Hey guys, very excited to be here, coming from Wild Western Sydney, where I'm working as a researcher in AI, machine learning. We do play a lot with mixed realities. We do create our own video games, although just educational games. Not so much fun, but still hopefully good. And most recently, we also started to work a little bit for robotics. But today, I want to talk to you a little bit on machine learning, and mostly how can you use machine learning in games. So I guess my first question for you, anybody already started to play around a little bit with machine learning? Is that? Oh, quite a few. Fantastic. All right, so what was the latest news that you heard that somehow interested you with machine learning? Anybody? Something that came up it was all over the media. It was about machine learning. There you go. The slides keep on changing themselves.
They're learning.
There you go. They're learning. Yeah. All right. So let me just jump right into it. I don't have much time. Probably the biggest news you guys heard recently is that the computer started to beat human players in a game called Go. This was estimated to happen around year 2025 because the complexity of Go is so big that we just thought it won't be possible with the current current computations. But yeah, it has been done, and it has far-reaching implications on what's happening in the world, and I'll get back to that. Also, we are in the era of self-driving cars. Everybody heard about self-driving cars. That's also happening because of machine learning, right? And also we have other news, for example, which are talking a lot about ethical conscience and ethical implications of machine learning and so on. I'll get back to that as well in this presentation a little bit, all right? So what essentially is machine learning? Machine learning, with traditional computing, what you do, you create a computer program, some object-oriented program or whatever, that you give it some input and it produces by itself output. So everything is controlled by you. With machine learning, the idea is a bit different. With machine learning, you provide a simple code, or not so simple, that takes some input data, processes the data, and then learns to perform specific actions depending on that input data. So once the computer program learns, it is able to solve similar problems to the data that was input previously, right? Where does it come from? Well, as you know, that machine learning is a sub-science of artificial intelligence, or it's spun out from artificial intelligence, which was started sometimes in 1950s, and it's quite exciting for us because we still can meet makers of our science, where mathematicians can't meet Pythagoras, but we can, and it's really exciting to talk to them. And then, you know, sometimes 1980s with invention or introduction of PCs or more accessible computers, machine learning came along. The theory of machine learning goes back to 1950s, 1940s even. I'll get back to that as well. But it wasn't possible. You can't do machine learning on the piece of paper, right? Because it's a human learning, essentially, because you are actually learning with algorithm, right? So you need actually machine to do machine learning. So once we started to have more advanced computers, we could start working with machine learning. And then along in 2010s, so not so recent, but quite recent, deep learning came along. So that's another huge buzzword that you guys keep learning about, the deep network, deep learning, neural networks, all of those big buzzwords. They are all part of this deep learning group. And fun enough, it's all just a little sub-science of machine learning, but this little sub-science of machine learning twisted this whole picture about 180 degrees, and now actually AI is considered to be a sub-science of machine learning. Why? Because artificial intelligence, in its sense, in its history, was always working on very smart algorithms that would perform better than humans, right? So we were continuously working on better algorithms and incrementally making better performance. While now, all you need is just a huge chunk of data, big computational power, and computer will essentially perform better than any of the best algorithms that humans have ever created. We can already see it, for example, in classification of pictures, right? Computer vision exists for many, many years. Since artificial intelligence, machine learning came along, there is a science called computer vision, and it performed quite well. The guys came with an excellent amount of algorithms, but only until 2 years ago, the Chinese company called Baidu finally came with an algorithm based on deep learning that actually performs better than humans, right? So, and just because they had enough data, some good ideas, and perfectly constructed deep neural network. They beat it humans, and they beat it all those scientists with years and years of experience, and they beat it the algorithms, right? So that's how powerful it is. So how does machine learning works? The process, guys, it's super simple, where you basically are trying to solve a problem. So let's think about a problem, not from gaming. For example, you have a company which is trying to predict sales, right? So how you have, for example, inputs on how much money you spend on R&D, how much money you spent on marketing, how much money you spent on administration, and you have the data retrospectively for, I don't know, last 50 years or 20 years or 30 years, so on. So what you do, you separate the data into two bits, into your training set and your test set. And then you use machine learning algorithm to somehow process your training sets to understand what is the relation between your marketing, R&D, and administration, and your profit that you made that year, right? So that's what you do with the training set. So machine learning, you somehow creates the model of prediction. And then you use your test set to see how good your model is. And if your model is predicting actually good numbers from your test set, then you know that your model is great. And you can start making predictions and questions for further years. What if I cut down my cost on R&D and increase my marketing spend? What if I cut down administration, right? So that's what is the power of machine learning, where you use your training data to train a specific algorithm, which builds a model of predictions, and then you can use your input data with your algorithm to make predictions. It's as simple as that. So in video games, if we take an example, what you can do if you have, for example, an online game or a game where you have a consent of your user to collect data about their performance, you can learn from the data that you collected from the user to come up with a prediction. So for example, if you have that very popular pay-as-you-go or the free-to-play model, you can somehow learn which types of users are more keen of giving you money for your game, or what are the assets that are the most appealing to which group of users. So you can actually create some targeted marketing and so on, right? Not so clean, but you know, it's part of the game business. You need to make somehow money. It looks simple enough, but unfortunately, there is just not one solution that fits all the problems. There is not one machine learning algorithm which takes the data and you can somehow magically make the predictions, right? It unfortunately looks a little bit like this, right? So this is a machine learning somewhere in the middle, and we have three major groups of machine learning: supervised learning, unsupervised learning, and reinforcement learning. I'll just give you a little bit of intro on these two, but this is the most important of video games. In supervised learning, it works in a sense that you know your inputs and you know your outputs. So the example that I gave you, you know that you have this kind of features of your spending on marketing, on your R&D and so on, and you know also your profits. So you can build a model which can be validated somehow, right? So you know whether your model is performing well or not. So that's called supervised learning. And you have two different things, two different sub-sciences here, which is regression and classification. Classification works, basically, you know, you have a big chunk of data and you're trying to classify where the different parts of the data are coming to. This is, for example, what deep learning is when you're classifying images. You have a giant group of images and you're trying to find all the images where is a pink unicorn or a crow sitting on the roof, right? So you are able to take incredible amount of data and classify it into predefined categories, right? So you know these are the categories and suddenly this magic algorithm classifies it for you. And you have these other examples, right? So you can classify images, you can detect fraudulent documents, you can study the customer retention, perform different diagnostics. The other big group is regression. This is model, actually my first example, where you're trying to find correlation between the models in your, between some data in your model and some questions you are trying to ask, right? So you can build, for example, model for the weather, right? So you just analyze all how the weather was behaving in the last 150 years, and then you know what's happening today. So you can just look at the previous experiences and make predictions about the future weather. Same goes for market, for population growth, and so on. So this is very powerful, and this is probably what most is happening currently in the world of machine learning. The other big group is unsupervised learning, where you don't know your results. That's where you're trying to find out somehow, you're trying to find the meaning of the data. And that's two big groups are clustering and dimensionality reduction. With clustering, you're trying to somehow find the groups of the data that should belong together. So for example, you're trying to find, that was my other example, right? Trying to find users who are most probable to buy specific parts of your game, most probable to buy the DLC for your game, who's going to spend more hours in your thing. So you're trying to find those groups of people and trying to find the meaning why. And the other big group here are the recommender systems. Right? So you can think about it, you start using a specific service. Service is collecting the data of your behavior, and then the system is telling you, all right, so why don't you also download this game? Because you probably will like it. And how does the system know? Because you know that you belong to the same group of users which have a similar behavior as you, and then those other users have bought a similar game, or they liked a similar game, or they did something, right? It sounds all super complex, but there are many different libraries out there. The most powerful one is scikit-learn, sklearn, and the other one is from Google. Just fell out of my head. And you can do all this with a couple lines of code. As funny as that, right? So all you need to do is meaningful data, knowing what your data represent, and you can program it quite fast and efficient. Literally, it's several lines of code to come up with all this. And then finally, the biggest group is the reinforcement learning, which basically is a continuous learning. It works like similar to the way we humans work, where we are either punished or rewarded for our actions. So if we do something great and we do it properly, we get reward. If we do it bad or we do incorrect actions, we get punished. And this is exactly how these algorithms work, right? So for example, here we have a game AI or robot navigation. So if it works like in loops, right? So you allow the robot, for example, to go just in a specific direction. If the robot hits the wall, you punish it. If the robot makes it as fast as it can, you reward it. And then the robot continuously with several loops of learning finally creates its model of behavior in which it should act. And I'm gonna come back to this later in this reinforcement learning, because this is the most important part for video games. All right, so what is, I just wanna get back to this really big word that you guys are probably hearing about, the deep learning. And what is the difference? Machine learning in its sense it's easy. It's because the algorithms are there, the libraries are there. For you, the most difficult bit is actually to come up with the meaningful data, the model of the data which you want to give to the machine learning algorithms. If you do not understand your data, you cannot have good machine learning outcome, right? And the big part of making sense of your data is extracting features, right? So I have this really nice example of, for example, example of recognizing motorcycle in pictures, right? There are many different motorcycles out there, right? We have choppers, we have naked motorcycles, we have race bikes, we have 3 cycles, we have many different motorcycles, different brands, different colors, different materials, different sizes. So it's really difficult to say, okay, this is a motorcycle and find me this kind of motorcycle in all the pictures. Instead, the way we work, and it's also in our head how we work, is we dissect the motorcycle into parts, right? For us, the motorcycle is something that has 2 wheels, has a I don't know how it's called, this thing that you can steer the steering rod. You have one light in front. It probably has a kicking pedal, has an exhaust pipe in the end. So you somehow dissect the motorcycle into lot of different parts, right? And what you do, you put those words, those parts into something called bag of words. And then you use that bag of words to teach the machine learning algorithms to find these features. More features the algorithm finds, the bigger probability that there is a motorcycle on the picture. Make sense? It's quite straightforward. But what was machine learning struggling with is because you needed quite good scientists to understand how to extract those features, what those features should be. So in classic machine learning, the feature extraction had to be done manually before you started to train the algorithm. And that's why it was super complex, and it was super tedious, and it wasn't ringing that many bells in the world. Along came deep learning, which can do feature extraction itself. It basically takes all the hard work from yourself. All the deep learning needs is an input and output. So what you give to deep learning algorithm is, for example, 100,000 images, random images, and then you give it also the answers in which of these images the motorcycle exists, right? So we say in out of 100,000 images, on these 25,000 there is a motorcycle. And then you just throw a deep learning algorithm on top of it, and then the deep learning algorithm, through several hours, days, months, it will just keep on improving in performance until it finds a perfect model recognizing those motorcycles in the pictures. Does this make sense? Yes? It's quite simple, right? So no longer you need to manually specify these are the parts of the motorcycle. Instead, algorithm does everything for you. And that's why nowadays you have a website where you can just tell them what you want to do, and those people with a little bit of money, sometimes even for free, they just somehow a little bit tweak the deep learning model, and it will do exactly what you expect it to do. You just give it enough data, and they will train it to you and give you the whole model for you to use, which is executable file, and it has an input and output. All right, so it's really cool. And then just this is another example. This is how neural networks looked up until 1990s. Up until 2010. That's when the deep neural network came, which basically it's called deep because it has more of these layers. These layers represent input, these layers represent outputs. So these are, for example, all your features. These are your images. These are some processing, some code, and this is what your output is, right? So that's the difference. It's just something interesting. I apologize, my slides were a little bit bonkers because I had them prepared in a different program. So a little bit of a history of machine learning before I dive into machine learning in games. This is year 1949. That's actually the first article published about machine learning. So I told you it was way before the actual computers exist. Well, there were computers, but they were about the size of a living room. So this is 1949. So this is even before ENIAC. And this guy, Klaus Shannon, he's actually founder of anthropical sciences and information sciences, big guy, and he published an article about programming computers for playing chess, right? But it took another almost 40 years to actually have a computer that could beat human players in chess, and you probably heard about it. It was the Deep Blue, the IBM computer, and it took about, I think, $8 million and several tens of researchers and several years of doing so to create this computer, right? Then it took almost another 20 other years for people to start taking machine learning seriously, right? Up until then, it was just something from the science fiction movie, something that was very unreachable, something that wasn't palpable for most of the people. Because in here, when somebody tried to explain to you how they programmed Deep Blue to win with Garry Kasparov, you would go after 2 minutes like, oh, just leave me alone. Even I wouldn't understand it because it's just so much. It's a combination of expert systems and a little bit of machine learning, and there's so many technologies behind it. But 20 years later, guys from Google, it took them about 2 years only to be the best Go player in the world using the deep learning technology. Right? So these are the guys that made it super popular. And after that, it just unraveled. You found this news that AI learned to play games from watching human players, right? So that was an AI that was watching human players play old Atari games like Invaders and all those other games. And just observing it, it mastered the game, right? So that's something palpable for us. If I can have a technology that learns from watching me, that's something that I can use, right? So it's no longer this complex thing happening. 2016 was the year zero for us, where the AlphaGo beats the best Go player. And it's super significant in the world of AI because the number of possible movements in Go is tremendous, right? And then the intelligence that beat the player actually showed the signs of creativity. There were other major things happening. And it took only a year later, 2017, when they created another AI that beat this previous AI, right? And why is it significant? Because this guy in 2016 learned the data was from existing human games, right? So basically, Google researchers recorded about 200,000 different Go games, and they let a computer to learn from human players. This guy, AlphaZero, learned from itself. It started from scratch. It only knew the rules of the game and started to play games with itself over and over and over and about 2 million, 3 million times. And just playing with itself, it actually devised better strategies than any human out there. Right? So it's kind of scary, but it happened. And it beat it like, I think, 6-0. So it didn't give a chance to AlphaGo. All right, so we're finally back in games. Right? So why is machine learning important for games as well? Not important, but maybe interesting for games. One of the big things is if you use reinforcement learning, you can create very nice adaptable games. Suddenly you are given this whole opportunity of analyzing your player behavior and altering the strategy or tactics of your game, right? Because for many, there are players who grok the game really fast and then the game becomes boring for them. And they just go and search for a new challenge and they just don't continue. That's why multiplayer games are so great, right? Because you keep on playing with human players. But for single player, this many times becomes a problem. Or the players are rubbish, and it takes them much more time to get in the game as to good players, right? Which happens to me a lot. I know how frustrated I was with Demon Souls, which was ridiculously, difficult game. So with reinforcement learning, you can actually use this approach, which I explained it to you, where you either punish or reward your NPCs in order to adapt their behavior, right? So if they keep on killing your player or keep on, giving blows to the player that are just killing him all the time, you keep on punishing them for it because you don't want to be too bad to the player, right? You need to somehow devise the good strategy here. That's the biggest point. You don't even have to. You are not limited to changing just the strategy. You can also change the whole environment, how it is generated, which I'll get back to when I start talking about procedural generation, right? So you can alter the way the difficulty of the game, so meaning like how many elements are dropped, how does your level look like, how many enemies are appearing, and so on. Right? So you can just keep on analyzing the behavior and build a model directly for your player. And if these things talk together and games talk to each other, you can even have games that cooperate using this model and sharing the user profiles and generating games very, very straightforward. So some players can even skip the initial learning part of the game because you knew that they are just really good in, for example, RPGs. There are many problems with this, but they can be overcome easily. For example, the mimicking stupidity, where players in the beginning usually they're rubbish. So if you use this learning model too soon, you basically learn that your players are rubbish, and it takes a long time to adjust back to the normal neutral of the game. So you need some like a reset button to say, okay, this is the moment I'm starting to learn from the player. The big thing is the set behavior, in which the game, for example, devises the perfect strategy against you when you're too good, and it no longer becomes creative because it thinks it found the perfect strategy and it will just do always the same. For example, the right hook, because it's the one that player is not too good, right? So it no longer becomes creative. And there are other problems in it. But this is a very powerful concept that is being explored a lot, and I'll get back to that with Ubisoft, for example. There are other things, which is the personalization of user experience from behavioral data, which means it's similar to the previous thing, but this is more connected to the narrative of your game, right? Usually what happens in the games is the narrative is set. It's a static narrative that goes from point A to point B. There are games such as, I think, Grand Theft Auto or other ones, which introduce this a little bit, where they analyzed your previous behavior and they adjusted story for you, right? For example, Witcher did it and so on, but Witcher wasn't too great in it. It was still quite static there. But basically what you do, you analyze how your character behaves, and then depending on the behavior of your character, you generate new stories for your character, something called the combinatorial narratives, where you can basically, if you have time and so on, you can just create a bunch of different stories, and then using machine learning model, you generate new stories for your user. There are many good papers on this. I strongly encourage you to look at them. And they come up with a pretty awesome solutions of how you can do that, right? So there are existing models that can help you to deal with this problem. They can also help you to improve the natural interaction with your NPCs, where you just won't have always the same response from your NPC. That's what happens most of the time if you play a single-player game. But you can get a very new, very refreshing responses, right? Basically also reflecting how your character behaves. If you are, for example, this good salvator of everyone, he can be really kind to you. But if you are this mean bastard that keeps killing everybody on sight, probably the people should run away from you and just react differently, right? And all this you can learn from the user behavior. Problems are here. The big problem is that you are losing control of your game, right? Big game studios spend a lot of money and time to perfectionize the experience that the players have when they play your game, right? They take a lot of time and effort to make sure that the experience is balanced, that it goes with the moment you are increasing your level, your experience becomes a little bit of hard, but not too hard, so your jumps are perfectly even, so it's nice and smooth. With this, you no longer have that, because every user plays a different way, has a different strategy. And some of them, if they are too dark, they can end up in a very, very dark place where the games becomes too mean to them and they just don't want to basically continue anymore, right? It happened. There are also papers on that. We can see that, right? And then the very big thing is also that if you look at the biggest advances in AI and machine learning in past 15 to 20 years, 30 years, they are always connected to a game. Whether it's a board game, it's a video game, it's always a game, right? People beating chess player, game. AI beating chess player, it's a game. Beating Go, it's a game. AI learning from people playing games, it's a game. You get it's a quite simple correlation, right? So games are there for scientists and for people to find new ways for AI and machine learning, right? So, for example, they say that for AlphaGo implications from 2016, they say that up to 40% of blue and 60% white-collar jobs are going to be threatened in the next 5 to 15 years. That's nothing, right? So we're already talking about fourth industrial revolution, where we're already trying to find the new job markets for people and create a new position for people who are going to lose their job. Eventually, it's going to happen. So so this is a big thing, right? So industry is always searching for people who know AI and machine learning, and many of them are coming from game industry. So if you are interested in machine learning, where would you start if you do games? This came out only a couple months ago, but I think it's a fantastic initiative by Unity. And if you guys use Unity, they built this small library called ML agents, machine learning agents, and they came up with those really bunch of cute little examples where they show you how you can train agents for Unity. Right? So for example, this is an example of how they train Unity thing to balance a ball on the board, right, after 30 seconds. And the way it works is that you have a Unity running on the front end where you have your agents, and it's connected to Google machine learning program. It's called the TensorFlow. I finally remembered. And then basically you train your model in TensorFlow and you feed it back to Unity, and suddenly after 30 seconds you have something that automatically balances a ball. Imagine how long you would spend programming that in Unity. It probably take you a significant chunk of your month, right? And this took 30 seconds to come up with a nice model that is executable in Unity, right? So I strongly encourage you that there is also, I don't have nothing to do with Unity. I just really am glad that they came up with an initiative like that. There is also a challenge they just launched recently, so you can become part of the challenge as well. And also Udemy has fantastic courses on machine learning. They're just spectacular. They are super cheap. They cost like $15 for a course with 240 hours of video. And this is actually which I've done as well because I wanted to show it to my students. and it's just great. I mean, it brings you straight to the point, cuts out all the technical things that are not important for you. If you do have a mathematical background, you just get right into it, and you can start building machine learning models straight away. That is a bit scary, yeah. Right. Okay, so let me just get really fast to the second bit, which is the procedural generation, which is connected to the machine learning bit, in my opinion, somehow. This is just messed up slide. That was my question for you. Whether you find level design easy and fun, the most exciting part of the video game project, or time and hungry monster, which would be the best, A, B, or C?
Easy and fun.
Easy and fun? All right, lucky you.
If you're the prettiest, so you would say time and money.
All right, that's what I was aiming for, right? So creating your levels, if you do create your games, takes a significant amount of time, right? And making it nice and balanced, it's a problem. So that's why, wow, that's a surprise. That's why there is a procedural generation. I don't have to introduce this whole sentence. I guess pretty much everyone has the idea of what the procedural generation is. It is a way of automatically generating your levels. This is an example of like how the old ways, how you can, for example, generate a maze for your game. This is based on completely random numbers using something called the Marx algorithm. So you can generate your mazes and dungeons. You can generate your terrains, right? So this is something called the fault line terrain generation. It takes only a couple seconds to execute, and you have quite nice terrains, right? So you use a fault generation algorithm, and then you apply Gaussian smoothing to smooth out the edges. Right? It looks, but it takes because it's visualized. It takes so much time. It usually takes a fraction of a second to generate the whole terrain, right? So that's another way of how you can, for example, generate the terrains. There are many other algorithms for generating your terrains. One of the easiest one, which takes about 15 lines of code, is just take a random height map, put the random white points on the map, and then smooth out your results. Right? Simple as that. Then the other things are using fractals, subdivisions. I can give you. I'm running out of time, so I can tell you all about it in private later. But the very big thing is noise functions, right? Something like this you can generate with one line of code, very, very nicely even spaced out noise. And then you can use this noise, for example, as your height map to generate your height map. Again, it's just one line of code. And then you can even use it for texturing your stuff, right? So you can create very nice blends in your terrains, right? So you just combine your grass texture with your dirt and the noise function as a mask, and then you have very nice terrains without any work and spending hours. Sorry about that in UX. So you don't have to spend hours on painting your terrains by yourself, right? And then the next big thing is shape grammars. Shape grammars and L systems work with a very simple concept where you have something called the shape rules. So this is a simple shape rule in which you have, for example, a rectangle, and then when you find the rectangle in space, all you do, you create a copy and you rotate it by 90 degrees. So when you do that, I found the rectangle, I rotated the copy, but what happened? Suddenly there is a new shape in here, and I can just apply the very same thing to that shape, and I can come on, and as you can imagine, this becomes, again, this is PowerPoint playing tricks, but something like that, right? And you can imagine if you combine more of those rules, you can create very complex, specific shapes. This has been used for very cool purposes. For example, there was this American architect called Frank Lloyd Wright, who was supposed to be ingenious architect, and he's dead for about the last 30, 40 years. And they've created a grammar that analyzes his work patterns, and now they can generate Frank Lloyd Wright's houses, even though he's dead, right? Using his way of making houses, right? But of course, even in games, there is this company called City Engine. Maybe you guys heard about them. They are very, very big in generating the cities, the whole cities from layouts of the city, and they are using exactly this kind of system: the the shape grammars combined with L systems, right? And what you're seeing here, there is just a bunch of rules in play. And all they do, they are just resizing how tall and small the building with some animations on top of that. But this is just done automatically, just from the rules. So they know that they have about this big bounding volume to play with, and they fill it with whatever shape they have in their shape grammar. And they start pushing it down, and those shape grammars, they even study them how the architectural stuff should change from one way to another, right? So this has been applied in quite a few movies, quite a few video games, and also, luckily for our scientists, also as a part of scientific projects. So what you're seeing here, there's also a really cool video online, is a map of Pompeii. That's a city in Italy that has been buried by Vesuvius. And they basically just used 190 shape grammar rules to generate this beautiful whole layout automatically just from the layout of Pompeii, right? And they populated with age, and it's beautiful. They did the same thing for Rome, somehow related always to Italy, but it's just what it is. Has been used in movies like Cars 2, a bunch of Pixar stuff. In games, I don't really know right now, but I know it's been used in games as well. Would you know what is the procedural game that every one of you has played? I'm 100% sure. Something that is procedurally generated every single time you play it. What will be the game? What? Minecraft?
What? Is that the right answer?
No, Minecraft is procedural generated?
Yeah.
Really? Okay, I didn't play Minecraft. How about something that everybody has played? I didn't play Minecraft, for example. I'm 100% sure that every one of you played this game.
Minesweeper?
There we go, Minesweeper. Alright? So that is the game that anybody didn't play Minesweeper? You didn't? Alright, so we have it for number one. Okay. But this is the typical example of a procedural game, right? Where you have a few different levels, and then this is actually using also something, it's not a shape grammar, but it's a simple system of how you place the bombs meaningfully onto the canvas for you to play it, right? And then, this is probably the worst artwork I found, but I was just asking, why can we be friends? The thing is, the procedural generation can play really well with machine learning, as you can imagine. If you can isolate your features which are using to generate your game nicely, you can very much use machine learning to generate the level for your user per user, right? So if you have a user who prefers vast open spaces where you can roam around, there you go. If you prefer a user who prefers spatial with a bunch of jumping and so on, there you go, right? And you can combine the learning from the behavior, from the user performance, and so on, and you can procedurally generate levels per user, per user group, and so on, right? So this can play really, really, really well together. And that's it, guys. Thank you very much, and I'll take your questions.